future is not set. Visual decision-making with predictive models. To talk about the future and prediction, I'd like to first bring you all back to 2009, the year I was applying for college in China. The system in China roughly worked in this way. All universities look at only my score in that year's national exam, the Chinese SAT, but there is only one exam every year. In theory, I can apply to multiple universities, but in the reality, I have only one opportunity to apply to one university. So to make sure that I go to the best university, my parents and I look at physical data and also had lots of discussions. Eventually, we narrow it down to two universities, and let's just call them R and S. R is definitely stronger in computer science and also located in a nicer city. So let's look at this together. We know my score in the exam, and we also know physical data, like the ranges of the scores could make it in 2008. The minimum score is usually a cutoff, a threshold. If my score would be higher than the minimum score of my year, I go to college. Otherwise, I fail. I would have to stay at home for another year and retake the exam next year. Given this information, I'd like to ask my audience to put yourself into my shoes. You don't have to answer this aloud, but if you were me in 2009, which university would you apply to, R or S? It's a difficult decision, right? For me, I was thinking about applying to our university because I feel my score is good enough for both, while I definitely want to be in a stronger department and nicer city. However, my dad is a professor in physics, and here stories begin. So my dad first collected data of past 15 years and fit the first model to predict the minimum scores, which he then realized was almost impossible because the minimum scores vary with exam difficulty every year, which was unknown. And my dad then fit the second model, which used test taker ranks. So the minimum scores correspond to the lowest test taker ranks school admitted every year, and that data is much more consistent across different years. And based on this second model, the lowest rank R admits is usually around the 3,000th, while for S, this is usually around the 6,000th. And my dear dad continued fitting a third model, which gives a precise estimation of my rank in the exam, and it turned out to be about the 4,000th. So based on all the three models, I finally changed my mind and applied it to S University. This is not the end of my story, because about a month later, I got the offer and also found automation data for my year. This means that my dad's models were completely correct. If I applied to our university, I would have to stay at home for another year, and I would not be standing here today giving this talk. S is actually Shandong University, which is indeed where I got my undergrad degree. So back in 2009, I was just graduating from high school. I did not know that trying different models was going to be my research in about 10 years. But I knew that I learned two things. First, it is very valuable to have predictive information when making critical decisions. And also, it is important that we can correctly interpret the predictions. It has been 15 years since my conversations with my dad, and lots of things happened during these 15 years, and lots of modeling techniques have been improved or enhanced during these 15 years. For example, we have deep learning techniques and also very powerful large language models. And in recent years, AI, machine learning, and statistic predictions are very common in our everyday life. Examples include election forecast, and COVID forecast. And under this context, my research takes the user perspective here. I care about how users make decisions from predictive models. This is because on the one hand, all the models are never ever going to be perfect. They can make mistakes. And on the other hand, the human users can misunderstand or misinterpret a prediction. And these combined imperfections can lead to poor decisions with significant consequences. Examples include that over-reliance on auto-driving systems can lead to car accidents. And many people regret after the 2016 US presidential election because they did not vote. And here, my research tries to overcome these imperfections inherited in decision-making to help users arrive at appropriate decisions. And I do so by creating visualization to convey key information in a prediction, unifying my knowledge about the model with my insights from decision-making experiments. My research process usually involves designing, calculating, and implementing different visualization techniques, as well as designing human subject experiments and formalizing user behavior in the experiment. The models I care about include both machine learning techniques and probabilistic forecast. And my users are mostly the end users, especially the general public. More specifically, my research tries to address 4 areas of imperfections in the decision-making process. And I order them by what I think a user must cope with when making a decision along the timeline. First, a model can be wrong, such as some auto-driving systems, such as the machine learning algorithms can misclassify critical instances. And I design visual explanations to help users identify the model's mistakes and help improve their appropriate trust in the model. And second, due to our imperfect knowledge, our models are inherently uncertain. Instead of providing the truth, they provide an estimation of the truth, which can be a range of possible outcomes. And I design uncertainty visualizations for US election forecast, and I successfully foster the voters' trust in the election forecasting model. On the user side, we also have human constraints. First, we may not be able to precisely read a visualization, which potentially cause misunderstandings or mistakes. And I study how people perceive a visualization to help avoid perceptual level mistakes. And finally, our abilities to process information are constrained by our cognitive limits. And I use virtual techniques to improve people's memory capacity and to help them understand complex data. For today's talk, I focused on first 2 areas. And right now, let's look at the first kind of imperfection, model flaw. So a famous example of a model flaw is that some AI driving systems can miss the stop sign if it has graffitis on it. Although the human users can potentially override this decision if they have enough prior knowledge, it still can lead to car accidents. What's worse is when the human users do not have enough prior knowledge, such as riding in an unfamiliar city. So last year, I attended a conference in Melbourne, and that was my first time in the city. When I was trying to ride a scooter to an event, Google Maps directed me straight to a river. There was no ferry nor bridge. I was literally standing there and thinking about if I should swim across the river. Eventually, I decided not to do so because I did not want to get wet. I turned back and missed the event. So in both cases, we probably do not want to trust the model, not to follow its recommendation to swim across the river. And we can formally define users' appropriate trust in a model using 2 dimensions. The first dimension is model recommendation, which can be correct or incorrect. The second dimension is user decision. A user could choose to follow or not to follow a model recommendation. If the user chooses to follow a correct recommendation, or they choose not to follow an incorrect recommendation, we see that they have appropriate trust in the model. Other cases could lead to overtrust or undertrust. The problem is that if users do not have enough prior knowledge, while a machine learning model is often very complex, then how could they know when the model is correct or incorrect to foster appropriate trust in the model? Here is a hypothetical scenario for the human-machine team. The decision task for the human users is to classify unfamiliar leaves given a machine learning prediction. You may have some intuitions about different leaves, but if you don't have sufficient training, it's actually very difficult to get it right, even if you have a machine learning prediction, because the model might be wrong. Our solution to this is to give users explanations for the prediction. We show some examples select from the training set. These examples have ground truth labels, and they also tell us a bit about how the model arrives at this prediction. Here is an example of the explanations we generate for the previous prediction. The input node has been classified as a hazel leaf. And we show two types of examples. First, we show the most similar train instances from the same class. And second, we also show the most similar train instances selected from different classes. All these examples are from a k-nearest neighbors graph. So each edge here means they are nearest neighbors to each other. We can imagine that the decision boundary is roughly here. Now, looking at these two leaves, do you believe they are both hazel leaves? I also want to point out two other examples, because I think these three leaves share a very similar shiny texture. And if you look very, very close, they also share very similar edges, like this. For me, I'm very skeptical about this prediction, and it is indeed an incorrect prediction. The input node is not a hazel leaf. By just looking at the explanation, even though I do not have enough prior knowledge about different leaf species, we can correctly identify a prediction error. And to explore different visual explanations, we vary both instant representation and their layout. Besides the image representation we are seeing right now, we also use a root chart of underlying features to represent each instant and explore the grid layout and graph layouts. So for the results, I show you the rates of different types of decisions, and I show you different representations and different layouts. For appropriate trust, a higher rate means better trust. For overtrust and undertrust, a lower rate means better trust. So, also for the spirit of my talk, I show you all the results are also uncertain. I show 95% confidence intervals or critical intervals across all my slides, including the future ones. For this experiment about classifying leaves, compared it to the baseline without any visual explanations, our visual explanations increased appropriate trust, decreased overtrust, and undertrust. For the image representation, the human-machine team can achieve over 95% accuracy, which is much better than the machine accuracy here. So 95% accuracy is very high in the literature. I think this is because we carefully select the examples and also explore different design parameters. And these well-designed visualizations improve decision accuracy and avoid mistrust. And our visualization designs could be potentially applied to other datasets such as medical images. However, I think an important next step is to incorporate model uncertainty or confidence into the explanations, because showing people uncertain information is critical for their trust and decision, which I will show it next. So, I'm going to roll back our timeline to the 2020 US presidential election. For those who might not be familiar with US elections, they are pretty much between the Democratic and Republican parties. The two parties are almost opposite to each other on many dimensions, and voting in the US is not compulsory. Several states have very similar voter support between the two parties. They are usually called swing states or battleground states. Election day is the final day on which voters may vote, usually the first Tuesday in November, and the final day, 538, is a well-known website focusing on poll analysis, especially political polls. So in 2020, people who lived in the US were immersed in a sea of uncertainty and anxiety as they awaited the election results. 4 days after election day, several states were still counting their votes, which caused deep uncertainty and collective anxiety among the general public. These uncertainties came back during the 2022 US midterm elections. About a month and a half before election day, 538 predicted that the win probabilities were 36 versus 64 in Arizona. However, about a month later, 1 week before the election day, 538 predicted that win probabilities were 64 versus 36, so they basically flipped. It is important to note that in the same year, the Supreme Court overturned Roe v. Wade on June 24th. These governor election results would decide the abortion rights in the state. Now, who do you think would be the governor for the next 4 years? And if you were eligible for voting in Arizona, would you cast your ballot for the candidate you support in this election? It was also a long wait until 1 week after election day, the Associated Press finally called Katie Hobbs to be the winner. Now, are you surprised? Likewise, in every election year, media news outlets publish election forecasts and use uncertainty visualizations to show them to the general public. These visualizations are viewed by millions of people over time and across different countries. As we just experienced, it is important for us to know how these visualizations actually impact the general public in real elections. We know that emotions can drive people's political behaviors, such as voting. Trust in election forecasts can influence people's confidence in electoral systems. Showing people outcome uncertainties may change their intentions to participate in elections, or can be real-world consequences. Because we really want real-world observations for these measures, instead of common in-lab studies, I led a launch experiment during the 2022 US midterm elections. We used 530's polls and construct the Bayesian autocorrelation model to forecast government elections in 33 states. And using this model, I construct and maintain our own forecasting website. Using this website, our team extensively recruited about 1,300 potential voters from 15 different states, roughly balanced their partisanship and tracked them for about a month. Here I show the interface of our forecasting website. The link is still active if you want to visit the website yourself. So if the main page has a US map, if you click on one of the states, say Arizona, it brings you to a state page showing you a visualization of our forecast vote share distribution. We deployed 4 visualizations on this website, and we select these 4 because we think they are representative of our possible visualizations for showing US election forecasts. Right now, we are seeing the first one dot plot. So a dot plot subdivides the total area under the curve into image-sized units and draws each unit as a dot. Each dot represents one possible election outcome with 1% chance, and the most likely outcome is the tallest pile. To show both candidates' vote share distributions, we deployed two dot plot. Because this was indeed a very close election, the two distributions almost overlap, but after I separate them, you can see that the two distributions mirror each other. We also have an interval representation where gradients represent probability density. And last, we also designed an animation which we call it Plinko. It is designed to let people experience uncertainty. So each ball bounce here represents a Bernoulli distribution, and a sequence of bounces resembles a binomial distribution, which further approximates the normal forecast distribution at the bottom. On this website, we also embedded several questions to measure emotions, trust, and intentions using self-reported scales. And we also have other information such as pose and changes over time. Using this website, our team conducted a longitudinal experiment with 3 waves of data collection. So in wave 1, 3 weeks before election day, we collect baselines for emotions and trust. This wave lasts for about 12 days, and in total we collect about 1,300 responses. Several days after participants finish wave 1, we invite them to visit our forecasting website. This wave ran until election day, 5 p.m. In total, we collect about 1,000 responses. Due to the deleted vote counting in Arizona, we start wave 3, 1 week after election day. We invite participants to come back and visit our updated websites, where we show some of the election results on both the main page as well as each state page. So election results are part of our visualization. In 1 dot plot, the winner is one of the dots. In 2 dot plot, we show both the winner and the loser dots. In 2 interval, we annotate the actual vote shares onto the visualization, and in Plinko, we drop the winner dot with other dots to let viewers experience uncertainty again. This post-election wave ran from 1 week after election day to 1 day before the US Thanksgiving holiday, and in total we collect about 900 responses. For our forecasting results, our model correctly predicted 32 winners out of 33 states and was only wrong in Nevada. For our survey results, we used post-stratification techniques as well as the 2020 US Census data to get demographically balanced estimates. And indeed, people's emotions, trust in forecasts, and intentions change over time. Their positive emotion increases over time, so people feel happier, more confident, or more relaxed after election. And correspondingly, their negative emotion slightly decreases over time. Their trust in forecasts also increases over time. So they trust our forecast more when they actually see it, or after election when they know the election results. And finally, their intentions to participate in elections slightly increases over time. So people feel more motivated to vote or campaign for future elections. We also found strong differences in visualizations and partisan leanings. For emotion, here I show different visualizations. And this top half means that to what extent Democrats feel more angry or sad when a Republican candidate is predicted to win, as opposed to when their party is favored. And the bottom half shows that to what extent Republicans feel more angry or sad if a Democratic candidate is predicted to win. So looking at them together, we observe a strong asymmetry in how two parties feel against each other, and some visualizations can exacerbate this emotional gap. Similarly, for trust, Republicans are biased towards trusting a forecast that predicts their party is going to win. And some visualizations like one dot plot can further this gap and exacerbate polarization. Overall, our results are of very high ecological validity. Participants were immersed in real elections, and one of them said that this was a very serious risk for all states due to many voting on Roe v. Wade at the state level, which hasn't been done before, to my knowledge, at least in many of our lifetimes. It was important to many to voice opinions and to pay attention to the candidates on where they stood on the issue. Concluding from this work, visualizations you are seeing in your everyday life can influence the general public's perception and trust, and may exacerbate polarization in real US elections. This project also gives us design lessons, but before we can confidently give design recommendations, we have two other problems to solve. One of which is that when I was reading participants' comments, I realized that some of them were still mad at the 2016 presidential election, in which Hillary Clinton was predicted to win, but we know that she did not win. Some of them were mad at us because our forecast was wrong in Nevada. Think about a win probability of 85%. It means that out of 100 elections, Hillary Clinton is expected to lose 15 of them. So as time goes on, if we experience more elections, a probabilistic forecast is guaranteed to have the wrong winner. Since this is guaranteed, then how could we maintain people's trust after they see a wrong outcome? The other question we were wondering, as well, I think you might be wondering as well, is that besides what the people tell us what they might do in the future, what do they actually do? They may tell us they are going to vote in the future, but we know they are not going to do so. They may tell us they distrust a forecaster, but still choose to look at it in the next election. And we have strong evidence for this difference in perception and decision from a different experiment. So in the first question, we ask people, how likely do you think this candidate is going to win this election? This question measures perception. People's answers are almost identical to the true probabilities we told them. Well, in the second question, we give people two options and ask them which option do you prefer. So this question measures decision. In this second question, the internal probabilities we derive from people's decisions are completely different. If we tell them a win probability of 85%, they act as if the candidate is definitely going to win. And in conclusion, perception is not equal to people's decision. Combine these two questions together, our goal is to have forecast visualizations that can maintain people's behavioral trust in forecast over time. Again, this means that we are going to design different visualizations, but to capture or say to formalize people's behavioral trust, we are going to give them an incentivized voting task in which they actually take action and choose a visualization to follow. Their behavioral trust is then the probability of selecting a visualization, and I will detail on this later. So for these purposes, we use multicolor simulation and grid search to generate US presidential elections with different win probabilities, and all participants experience 10 elections with a mixture of correct and incorrect outcomes. Next, I will briefly explain how this experiment works. Before the experiment and before the 10 elections, I select which candidate I'm going to support in the experiment. Here my example support Davis, and I have 10 coins right now. I then see the first election in which the forecast says Davis has a win probability of 15%. I then decide if I'm going to vote in this election. Because Davis is unlikely going to win, I'm going to choose to abstain from this election. Then after election day, I see an outcome sampled from our forecast distribution. And surprisingly, Davis wins. I have more coins right now. I then decide which forecast website, which is essentially which forecast visualization to use for the next election. Here, I'm going to choose the last one, which is a text representation. And in the next election, the interface is updated accordingly. So this process continues. Our participants experience 10 elections like this, which is essentially a sequential decision-making problem. And we can derive people's we can derive people's probability of selecting a visualization from their decisions. We assume that people maintain a little trust variable in all the visualizations. Their trust according to what they have seen in this election. For example, if the forecast is correct or not. For other visualizations they have not seen, we assume their trust is the same, and this process continues. So the latent trust drives people's decisions and generates the probabilities of selecting a visualization via our softmax function. And because of this softmax function, we initialize people's trust around 0 in the latent space to avoid identifiability issues. These probabilities eventually generate which visualization people actually select in the experiment via a multinomial function. So the probabilities here drive people's decisions, formalize people's behavioral trust. To gradually refine our results, we actually conduct 3 experiments. Given the sequential decision-making model, people's trust is a function of the time point in the experiment. For example, for experiment 1, I aggregate all the 300 participants, and their trust is stable after 2 or 3 elections. And then eventually text and dot plot led to a higher level of trust the intervals did. I'm going to skip the details of experiment 2 and 3, but across all the 3 experiments, the most trustworthy ones are text and dot plot. Because we also found a strong partisan split in previous experiment, we then aggregate all the 10 elections and divide each experiment by different parties. Here, the results of experiment 2 and 3 are consistent across different parties. But in experiment 1, Democrats trust dot plot the most, while Republicans and other party supporters trust text the most. We continued dividing each party in each experiment by their educational levels. Right now, the x-axis is the highest degree people obtained. Then across all the 3 experiments, people who have a more advanced degree trust dot plot better, regardless of their partisanship. We know that in the recent years, the Democratic Party in the US has more educated supporters, and this educational difference could explain the partisan difference we observed previously. Given these results, we can now look at the media news outlets' current designs. The Economist used a text representation for their 2022 US presidential election forecast. And given our results, we think this is probably not the best option for maintaining their audience trust. While 538 uses a design that's very similar to our dot plot, and we think this design could build their audience trust in the forecast over time. There are many other ways to use our results. Here I give you one possibility, which is how I would do this if I were running a US presidential election forecasting website. My goal here is partisan neutral and trustworthy. And for this goal, I will combine text with dot plot to bridge viewers from different educational background. And my work also shows that giving people explanations for the model could foster people's appropriate trust in the model. So for this goal, I will add a link to my model explanations on the top of the page to encourage people to click on it. I will also allow people to switch between different options by adding these options on my website. And finally, I will continue collecting user responses by adding a short survey form on my website. These two election forecasting projects have direct implications and applications to the incoming 2024 US presidential election. So, we were joking that our results could be used by a website to encourage voting for a particular party. Well, this definitely raises ethical concerns. It also emphasizes on the importance of doing research to develop trustworthy and party-neutral designs. In the future, as a faculty member, I'd like to connect more with some journalists and media news outlets to work on this space. While we were doing these two projects and other election-related projects, we had been talking to a few different journalists, and we found this partnership is very useful for us and also for them. In the future, I think an important step is to move beyond the notion of forecast correctness, because from a statistical point, a forecast does not have right or wrong. The forecast quality is actually a continuous scale. And I like to work on this and also consider multi-party systems, such as the Canadian or the German electoral systems. And these are my works and plans to address model uncertainties in decision-making. Next, I will use 3 minutes to summarize my work on addressing user imperfections, including both perceptual and cognitive limits. So for user perception, the central question for me is how people perceive a visualization. For example, when looking at two scatter plots and comparing correlation between the two scatter plots, we think, or say our hypothesis is that you might be looking at perceptual features. And our goal is to formalize these features. Over these years, I tried different methods, such as large-scale questions, using a list of possible features, and also inputting the images into conversion works. We definitely have some evidence to suggest that people might be looking at perceptual features when making such comparisons. But I think what's more interesting is that I found that conversion works are not very suitable for visualization images, because they're designed for natural images. And in the future, I'd like to work with computer vision and graphics people to design model architectures specifically for visualization images. And I think this could help reduce model redundancy and improve training efficiency and accuracy. For users' cognitive limits, because virtual reality techniques provide us a huge space, I explored how to use VR to help people remember articles they read using mnemonic devices, and also explored how to show model outputs in VR. So, to summarize my entire talk, my overall goal is to overcome imperfections in decision-making to help users arrive at appropriate decisions. And I talk about model imperfection and user imperfection. For model imperfection, I talk about how we design visual explanations to help users identify model mistakes and improve their appropriate trust in the model. And I also talk about how we design uncertainty visualizations to convey uncertainties in election forecast to the potential voters, and we foster their trust in the electoral outcomes. The next steps could be to incorporate uncertainties into the explanations for machine learning models, or to convey forecast quality and consider multi-party electoral systems. For user imperfection, I talk about the potential techniques to overcome perceptual and cognitive limits. The next steps could be to design domain-specific architectures for visualization images or continue exploring opportunities in AR or VR. Behind all of this, here is how I maintain my future research agenda.